My name is Brien Blandford Levy. I'm a Partner Solutions Architect. So if you're not familiar with that role, it's to support our partner community like Eagle Dream in deploying for our customers. So I'm kind of just like a solutions architect, except that I focus on helping partners implement when they get into things. So those tend to be kind of complex engagements where the regular solution architects, though they may be involved as well, usually a partner gets involved when there's a decent amount of complexity. So we see a lot of I see a lot of mix between kind of standard solutions that involve straight up EC2 and kind of legacy systems like IBM systems or Hyperion. But I also see a lot of customers who are coming to the cloud net new and want to get started on the right foot, and they want to explore serverless. So what I thought I would talk about today, since it's always a hot topic, is not Lambda, because everybody loves Lambda and everybody knows Lambda. And when you think of serverless, you always think Lambda first. But what actually started AWS, and if you already know this story, then forgive me, but what actually started AWS was, I think, in 2001/2, when the seed was initially planted, and Amazon.com had a problem in that we had a giant Oracle database and we had a monolithic application running on top of that. And we'd been around 6-7 years and realized if we want to scale to the place where Amazon is today, it was going to be impossible, absolutely impossible. And the reason it was impossible wasn't necessarily even technology. It was that in order to make any change to that system, 10, 12, 15 teams had to be consulted. They had to put their input in there. How is it going to break what I do? How's it going to break what you do? And so forth. And it just turned into this giant mess every time you tried to add a feature or change something. So we realized we needed to decompose for agility. And if you've ever seen the standard kind of serverless deck, they'll talk about that, where microservices were something that Amazon went through, how we had to take this monolith and tear it apart and build microservices. And so because of that, the very first service was SQS. It wasn't an Amazon Web Services feature, it was a straight up Amazon feature, but it was for Amazon to use to break apart this monolith and have a messaging system between it and decouple those various microservices that we started building. And it built on that. The very next service, when AWS officially launched, which is, I guess, technically the first AWS service, is S3. And if you think about it, SQS and S3 are both very serverless. You don't manage anything. You don't provision anything. You don't tell it ahead of time how much you need, how much you're going to need. And when you start removing items from a queue, or you start removing storage from S3 and life cycling it, you stop paying for it. So by the nature of AWS, we started as a serverless offering and then started adding the traditional technologies like EC2. So I wanted to talk about those kind of services and how decoupling is such a key part of building microservices in a serverless manner. So if you'll indulge, I am going to go through two. They're kind of hypothetical architectures. They're based off of very recent customer experiences where I've been involved. And I kind of change things up a bit, one to sometimes illustrate a point, but also to kind of mask any customer design or architectures themselves. But we'll get right into it. So the first one here is imagine an IoT, machine data consumer customer, where they have a bunch of machines out in the field and they produce various data, and they're legacy systems too. So they could have pictures, they could have PDFs, they could have CSV data, they could have some kind of proprietary data written in binary. They could have large files, all of this stuff. Maybe they zip it, maybe they don't. They could have all kinds of things out there. And they aggregate that data in S3. And this is the full architecture. And what I'm going to do is deep dive each of these pieces. So they wanted something to be event-driven. They don't want to pay for these systems that dump data once a day or twice a day. They don't want to pay for resources lying around the whole time it's not being used. But they also want it to be near real time. Whenever customers ask me for real-time systems, the very first thing I say is, what do you mean by real time? Is real time on the order of microseconds, or is real time on the order of seconds or minutes? Like, what does that mean? So when I say near real time, I mean the time it takes to kind of flow through this. That can be, let's say, under a minute, but not more than 15 minutes at any time. So somewhere in that range where you expect data to land in a reasonable amount of time. And I kind of consider that where someone who's sitting at a web page waiting for it to load a big set of data wouldn't give up and go get a coffee. That's kind of what I define as near real time. But that could be, dependent on your use case and dependent on what the end result that you need would be. So here's what I'm going to do is go through each of these pieces and start talking about the questions that I would ask a customer when they are proposing a design, or a partner when they propose this design. Why did you choose certain things? So first off, why is IoT in quotes? So if any of you have actually dealt with IoT systems and they speak MQTT, I envy you. I rarely see that. Anytime we leverage the IoT platform, it seems to be that there's this middleman aggregator layer where there's some kind of either there's some kind of edge device that's an aggregation point, or there's different software that's a vendor proprietary third-party IoT device software. It kind of consolidates things, and you have very little control on those systems often. So the data gets aggregated and it gets dumped to S3 because it's often in a different system where they're going to leverage HTTPS or some other protocol, but not necessarily MQTT. So this is where this is why IoT is in quotes here, and this is kind of these legacy data systems that are dumping to a raw bucket. So that's going to trigger an event flow, and often we think of this put to S3 as a direct trigger for Lambda, and it can be for sure, but there's a reason to use a queue here. This symbol I probably should have said is SQS, and that's the raw queue. So this basically says anytime there's a put to S3, dump that data onto an SQS queue. And the reason for that is actually Lambda triggers from S3 are not guaranteed. I don't know if you've ever looked into this deeply, but AWS does not provide an SLA for that. We say if you experience a failed event trigger, cut us a Sev2 ticket, but you've got to really kind of have your documentation around and really be able to see that happen before we'll trigger an SLA on that. So it's not guaranteed, but you can have it go to SQS. And that also is not necessarily guaranteed, but we'll talk about how you can sweep. So the other benefit here is that say that you have, I don't know, 10,000 puts in a single second. That can write to SQS no problem. There's no documented limit on the number of message puts to a queue. So easy, you can dump 10,000 messages to that queue right away. And these are small messages, right? This is just an event. This is a file name in S3 that got put to S3. So Lambda can then cycle through that. If you were to try to trigger 10,000 concurrent invocations of Lambda, you would have to ask for a limit increase. The default is 1,000 in an account. So if you have Lambda elsewhere down the line, you could also break a lot of your flow here. So by putting it to the queue, you can allow Lambda to do its work over time and start exhausting that queue and pulling data out of it. And if there's any failure, it helps too. If there's some kind of weird thing that got put to S3, you can write it to a dead letter queue, and humans can go take a look at it. Another system could take a look at it. You can figure out what's going on. So this builds a lot of those complexities that you might not have necessarily thought through until you run into it. It kind of handles that for you by writing to SQS. There's other ways to get data to S3 here. You could do this over a VPN, over DX. There are, if you're not aware, I don't know if this is sensitive, but there are new gateway interfaces for S3 that are coming that effectively leverage private link. So you can have a DX connection put directly to S3 without traversing any public endpoint. There's also other ways to do that with API gateway or a proxy in front of that. So there's other ways you can get data from these legacy systems directly to S3, and it makes it very versatile. And once the data lands in S3, you know it's there. So I mentioned that those event triggers aren't necessarily guaranteed, and it's often recommended to have a Lambda sweeper come through here. So you could have another Lambda off to the side that just sweeps a prefix and says, hey, has that event been processed? If this function processes an event on this queue, it can then sweep that prefix and move it to another one, call it, pre-processed or unzipped. It can just move that object around, and then another Lambda could come through and sweep and say, hey, did anything get missed? So that's the reason here to put a messaging queue to decouple even S3 from Lambda. And why didn't we choose Kinesis? Well, one of the reasons is these are really tiny little messages. They're not big. So SQS fits that message payload of 256 kilobyte maximum size pretty well. It also fits the price point. It's really cheap. And there are no limits to the number of messages here. So if you dump 10,000 a second or 100,000 a second, you can write those to that SQS queue, whereas you're going to maybe throttle on Kinesis. And you could also potentially have to reshard and deal with all of that. So SQS is very simple. It's a really good use case in this example. So then moving down through the architecture, say that we unzip, this this is some kind of zipped file package here, and it goes to this S3 bucket unzipped. And then it triggers another event and puts it on another queue, which goes to another Lambda. Same kind of thing where you could have this write to a dead letter queue if you wanted. You can have another Lambda sweeper and all of that, but it's just not shown here for simplicity's sake. But now we have a Lambda that fans out. And the reason that you can leverage a fan out here is these might be different file types. You might have CSVs, you might have PDFs, binaries, large files, all kinds of stuff here. So it's a really good idea to kind of really break this into microservices. If you find that there's a weird formatting issue in your PDFs, well, you're not going to break your CSV and your binary and your other queues. So it's a good way to kind of troubleshoot exactly what's going on. And another thing here is that this data might be really simple, right? The CSV data might be kind of formatted, it might be flattened, it might be good to go. There might not be much transformation. But a PDF, maybe you're going to call another service like Textract here. So it's good to kind of break that out so that you can make sure that you can segregate how these things perform, how these different queues perform. Why not use glue is a question that's always asked with ETL. And for actually this architecture that the customer proposed, that was the very first question I asked. And it's because of a few things. One is that near real-time feature that we wanted. Two, there's some complexity here, like the binary code that might be custom. It might not be written in Python or Scala. It might not be a package that the customer can really even dig into. Who knows? There could be a lot going on there. So glue is kind of tough to use. It also, even though glue has a new streaming feature, it kind of requires a Kinesis or a Kafka queue to feed data to it. So currently, glue isn't really set up to be that streaming ETL platform for this kind of use case. And the next one is this route row, and we'll talk about that. By the way, if you have any questions throughout this, as I dig into these architectures, please raise your hand, shout out, and just stop me. I'll try to remember to pause between slides so that you can hit me with any questions. If you think of something later, don't worry, and you can always ping me off on the side. Are there any questions so far?
Hey, Brian, there's two in the chat box.
Chat box. Let me see. How do I get to chat box when I'm sharing?
Should be probably down in the bottom toolbar.
Chat. There we go. Okay.
Perfect. Or one question. Sorry.
So, where's the question?
Well, so I could restate that question. I was just, you talked about triggers off of S3 not being reliable. So I guess my main question was, is whatever that data system pushing an object to S3 and then sending a message on SQS that refers to that object?
Right, exactly. So it's not pushing the object to this raw queue, it's pushing that metadata. So if you're familiar with Lambda, there's the event and the context. It's that event, right? It's that hey, an object landed, here's its bucket name, here's its object name, and its key, here's its some data about that object and so forth, when it happened and all of that. So I hate to use the word not reliable. It's very reliable. It's just that we don't provide an SLA on that. So we're not going to say that 99.999% of the time you're going to get those triggers put to Lambda. We don't provide that. So that's why I say it's a good idea to make sure you assume it's not going to work, but it's going to work for the majority of the time. But yes, you're right. So SQS here has a 256 kilobyte limit per message. I think there's a way to extend that via having that message body live on S3. And that's kind of what we're doing here anyways, is basically just taking that event trigger, that metadata, and then having Lambda go fetch that object. So this Lambda would go fetch that zipped file that's put to S3, unzip it, and do its work. Does that make sense?
Yeah, that's great. Thanks.
Cool. So the last little piece is a route row down here. And this didn't happen in this customer's architecture, but I saw it in another one, and I thought it might be kind of cool to show. So let's talk about what route row means. So what happens if you have a large file that exceeds the memory allocation of Lambda? So for instance, if we're unzipping a file and it's a gzip file, and it's, say it's 1 gigabyte zipped, it might be 4 gigabytes unzipped. How are you going to store that in Lambda's memory? It's, you can't allocate that much. You can also run into this on glue. So taking that example of gzip, gzip is not a splittable file format. So if you're if you're not familiar with Glue, it's effectively like a on-demand EMR cluster where there's different worker nodes. Those workers are called DPUs, data processing unit. And each one of the DPUs, it depends on some of the settings, but it's effectively a little sandbox worker instance that has a Spark context. And what Glue's real power is distributed compute. So it's going to take however many DPU assigned, say it's 10, and they each have 16 gigs of memory and some number of vCPUs. It's going to try to break apart the job just like EMR would and spread that out over all those workers. But gzip is not splittable. So if you applied I ran into a customer that had a 4 gigabyte zipped gzip file, 4 plus X compression. So that would be greater than that single DPU's memory of 16 gigabytes. But they had 10 DPUs assigned. They're like, why isn't this scaling? We should have 160 gigabytes of RAM complete among our worker nodes. But the reason is you couldn't split it, so you couldn't really do anything except leverage one single DPU for that. So I ended up writing some code for that to help. And the way that this works is this is kind of a little bit of the code that's important. I'll show you the actual code if you want to see it. But basically, we set up a get object from the S3 client. And then we start chunking it. So we take a chunk size here, and you can set that chunk size to whatever you want, 10 megabytes, 40 megabytes, whatever it is. You can then apply your unzip methodology or any kind of logic you want, and then do a multi-part upload. So each time we take that chunk and we unzip that little chunk, we can then put that as a multi-part upload to S3. And we'll end up with that nice big 16 gigabyte unzipped object in S3. At the end of that, you just have to kind of tell it, hey, I'm finished with my multi-part upload. So complete that and keep going forward. There's another way to do this where you can take this, if it's CSV that's under the hood, under the gzip, you can then read that CSV line by line and basically build multiple CSVs. That's actually a really cool thing to do for Glue if you're pushing to, for instance, Redshift, because Redshift is going to run into the same issue. If you try to issue a load command to Redshift, it's going to look and it's CSVs that are the source data. It's going to look to parallelize that over all of the slices on all of the Redshift worker nodes. So if you have 10 Redshift nodes and each has 3 slices, it could possibly load 30 CSVs simultaneously. So there's an optimum there, breaking those CSVs up from this giant CSV into multiples. So this would be code that could help you do that. And like I said, I could show you the full code for this. It did both, where it would take keep that entire large 16 gigabyte CSV, but also break it into chunks for optimized Redshift loading. So that was that row at the bottom here. But now we push that data to S3 CSV. Maybe this is, this binary ends up as CSV, this texttract output ends up as CSV, and so forth. And like I mentioned, we can load that to Redshift, and we can put it to a relational database using Amazon Aurora here. So the first question is, why use RDS proxy? Well, if you're not familiar, RDS proxy is a managed proxy layer that sits in front of Aurora, MySQL, and Postgres. And what it does is effectively establish a couple of database connections to your actual database writer node. And it keeps those open. It keeps them long-lived. And then Lambda here, maybe there's 10,000 Lambdas that spin up. I mentioned concurrency, but just say there's a bunch of Lambdas that spin up. Each one of those, if it's concurrent, it's going to be independent in its own little sandbox compared to the others. So therefore, it would have its own database connection. You could run into an issue where your database CPU maxes out just because it's trying to keep all these connections or build all these connections and tear down all these connections and so forth. So you could end up with a lot of orphaned connections. You could end up with a lot of overhead of trying to establish these connections to your database. So what RDS proxy does is handle that piece for you, and it can scale horizontally and handle quite a bit of simultaneous concurrent connections, but it maintains just a few from it to the database, and it can leverage those and write on those with many different like writes. There's a thing where you can have some connection locks that you have to be aware of, but nonetheless, it can be a way to scale a serverless architecture. And it was really built for making sure that this Lambda writes to a relational database can scale. So that's one pipe of where our data goes. The other pipe is to our data warehouse. And here we're using a loader function from Lambda that's an event-based or time-based to populate a Redshift table. And the reason that I would use Lambda here instead of Glue is that we already have all the ETL done. Assume that this bucket is pretty clean. These are CSVs. They're primed and ready to go for Redshift. There's not really a need for Glue here. You still could use it, but you don't really need that entire Spark context. And there's actually a package that's on GitHub, and you can I'll show it to you in a second, that leverages a Lambda loader, and it basically keeps in track in a DynamoDB table where files were, where they've gone, and so forth, so that you can keep track of what's there. That's kind of similar to like a Glue job bookmark. But this is a very cost-effective way to load Redshift. And it's kind of often a misconception that when you load data into Redshift, Lambda isn't doing the loading. Glue isn't doing the loading. What it's doing is issuing a SQL statement to Redshift, to the leader node, and says, hey, leader node, you go figure out how to load this data. And if it's on S3, Redshift says, oh, I need to put a query down to each of my worker nodes to go fetch that CSV file from S3 and load it in. So Lambda can actually massively parallelize this load command to Redshift and can offload that to the cluster. And then the last piece of this architecture is unloading this data to Parquet. So we could have done that with Glue. We could have converted CSVs to Glue. We could have done that with these Lambdas, but that's a lot of extra work here that we're going to have to pay for. And that's another piece of this cog that might break. So there's another function that can be applied to the Redshift cluster called unload. And unload can specify the target file type, which in our case would be Parquet. You could specify other things such as the partition key for that Parquet, the Parquet files, and offload that to S3. So this is a kind of neat architecture that, aside from the Redshift and the Aurora piece, are completely serverless. All the working in here is a serverless system. And it's based primarily on S3 and SQS, those two initial services that AWS had, with a little bit of Lambda spiced in there. Any questions so far? All right, so let me show you before the stop share, and I will share a different screen. So this is the Lambda loader for Redshift. You can find it on GitHub, and it's a CloudFormation stack you can deploy. And like I mentioned, it basically enables Lambda to pull from S3 buckets, write to DynamoDB what files it's already processed, so it doesn't go back through things, and then write to n number of Redshift tables. So I recommend that you look at this if you haven't seen it before. It's a pretty good option to look at instead of Glue. Sometimes I'm a big fan of Glue, but sometimes you don't need that full power.
Hey Brian, can I ask a quick question?
Sure.
You mentioned about the Lambda. It's basically, I mean, you're specifying kind of a source for the data, and it figures out how to get it in. And so is that one of those sort of asynchronous operations you can check the status on, or is it just eventually consistent?
So in terms of checking the status, you can configure when that Lambda invokes. So you can know when it's processing. In terms of the load to Redshift, that is an asynchronous event, I believe, where it will offload that to the Redshift cluster. So you can monitor that with the what are all those Redshift tables? STL tables that you can see what's been loaded. You can also query that DynamoDB database. If I go back to the architecture.
I haven't used Redshift before, so.
Gotcha. Yeah. So you can also query this DynamoDB table that it writes to and see what it has pushed. And there's a lot in this documentation on how it works and how it is configured. So yeah, I highly suggest you look through this and see if there are any possible use cases you would have for it. It basically is like Lambda's Glue, so to speak. So you can use it as a cron job or scheduled. There's a lot of different things here.
Cool.
Reviewing logs. Yeah, exactly. And the other cool thing is it can operate in your VPC too. So just like Glue with database connections, you can force the ENI to live in your VPC for private communication. All right. So that was one architecture I thought was kind of interesting. And the next one is another customer that I've recently seen where they have a lot of third-party systems. So these are the data systems over here. These are, assume this is a stock trader platform where they're going to do some analysis. A good hypothetical here is that a lot of stock trading platforms, especially the bot ones, do a lot of selling and trading based on minimizing your tax amount for your portfolio. So for instance, you could, if you had an index that has like tech stocks, like the FANG stocks, and they're all going down, you could sell them and then buy an index that's got almost the exact same mix, rebuy that right away, because you know they're all going to come back up. And you basically get to write a bunch off on your taxes without losing money. I had a colleague of mine say, I think he was using, I can't remember what the platform was, but he basically was up like 20% in his portfolio and got like 20% tax write-off. It's like, that doesn't make sense, but it's pretty cool. So just imagine that's kind of this scenario here. So this customer is ingesting from many other third-party customers, and they have limited control on what comes from here. So that might be XML data, that might be CSV data, it might be all kinds of stuff. So limited control, they could have big file sizes and legacy things. So that's kind of what we're looking at here. So let's start off here. Why would we use API Gateway to ingest for Kinesis and throw a Lambda in the mix? Well, the reason that this customer decided to do that is, like I mentioned, they wanted an XML response. They wanted to be able to provide different methods to their API gateway that have different integration response that all end up on the same Kinesis stream, perhaps, but they might support different kinds of data. So this is a good way to scale that out when you can't install the Kinesis client library on your systems here, when you don't have that much control. Maybe they're all kinds of things. There could be even be a file share here where you're going to have this data write directly to S3 and so forth. So this API gateway endpoint allows them to be very flexible on that and also scale in a serverless way. So all this Lambda does is just say, hey, I got some data. Am I good? Yes. Then write that to the stream. If not, throw an error back. There's a question of why not to use SQS here or MSK. And part of the reason is that like I mentioned with SQS, there's a limit on the data payload. So Kinesis is a really good option here. There's also a good way to scale this out that we're going to talk about. But it also provides the ability for multiple consumers. So right now, I'm going to show you just a single consumer on this stream, but you can have up to 5 applications consume this stream independently of each other, and you can even provide dedicated throughput to them. So if you had one application that's looking for how to minimize their customer's tax burden and give that data back to your end customers, that would be one. You could have another that could potentially look at like trends in the market and make real-time forecasts on those, or provide personalized suggestions for other indexes that customers could buy and so forth. So you could build a lot with this from the same stream.
Hey, Brien, another question or point of discussion. I mean, ALBs can be used to front Lambdas as well. And if this is just a really simple scenario where there's a single Lambda you want to invoke, and you could, I mean, is there a reason to involve the complexity of the API gateway?
Yeah, so an ALB is definitely an option. So part of the reason that they wanted this, I believe they had a lot of other responses here where this was going to be a proxy for S3 for file shares. So it would end up fronting as like a proxy for S3 there. They had other things with Direct Connect. There were a lot of other reasons for using API Gateway in the middle. But yeah, you could look at a potential for using an ALB as well. You can have different Lambdas invoked based on the path of that application load balancer and where it goes. So there's other options for doing this. But this was a pretty straightforward kind of approach to just a simple API that they could expose to their customers as well as a website. So a lot of other stuff was behind the scenes. For this specific little piece, though, we're going to focus on, that was the decision point for them.
Cool.
Okay, so once it hits the stream, there is a data enrichment Lambda. And so the first thing that this does is look at an external data source. And this was a location provider. So it effectively took in an address and gave you back like GPS coordinates. For our case of this stock trading platform, assume that this kind of correlates a zip code to a certain tax code. So this is going to enrich that data in flight with some specific tax information for their locality. So like I mentioned, I live in New Jersey, and the taxes here are way different than in New York City or in upstate New York. So you can imagine that my tax strategy might be very different than another person's. So we didn't actually go directly to this external data source. And the reason is that it could be really slow. So sometimes those responses could be greater than a minute. And if you have data in flight in a kind of near real-time system, it provides a bit of complexity there. That's also a reason that you might not want to use Kinesis Analytics. First, we're going to enrich all of this data that comes in. So there's not really a branching kind of output that we need where some data we could put on this way and redirect it to a different stream, and some data we could redirect to another stream and so forth. So Kinesis Analytics was ruled out just in that it's not, this kind of happens independently of this queue and needs to be able to take a while. The problem though is this queue could fill up. So Lambda could take a long time to kind of process here, and if it's not able to process as many records as are coming to the stream, you might be stuck with a bunch of pileup in that. The other thing I didn't mention is that the customer wanted this to be able to scale out. So they might have quite a bit of ingestion that would rise and fall. Order was very important too. So one of the reasons not to use SQS is that if you were to use SQS with ordering, you'd have to use a FIFO queue, and there's a limit of 3,000 puts to that per second. Kinesis per shard has that limit, but you can increase the shard count dynamically. There's also features coming where right now to increase the shard count, you have to keep a CloudWatch metric, look at that stream and see if you are running into your limits. And if so, trigger a CloudWatch event that triggers Lambda that reshards your stream. There's more on that coming with Kinesis where we'll handle a lot of that for you. That's the only thing I don't like about Kinesis that I would say doesn't make it truly serverless is resharding. It's kind of like if you looked at a shard as an instance, it's kind of like you telling Kinesis how many instances you think you're going to need. So it's kind of like an auto-scaling group, but Kinesis is getting more and more serverless every day, so we'll get there. And I mentioned that the payload might be pretty big, so SQS was kind of an out for that one. So in order to speed this up and ensure that Lambda didn't fall behind the stream here, what we did was actually use SQS. And so when this ingestion mechanism occurred, we would say, hey, just throw that location data to this queue and then populate this cache. That ensured that we'd always get cache hits from this enrichment Lambda. This was a pretty simple way of making sure that that external database wasn't a bottleneck. And we're going to talk about how Lambda scales out in this instance, but this caching strategy was necessary that could break a lot of downstream things. Are there any questions so far? All right, so continuing on down the line, that enriched data goes to a DynamoDB table and then on to the end consumers. But we wanted to keep some of this initial, the raw data and dump it to S3, and then take that enriched data and also dump it to S3. And Kinesis Data Firehose is a great idea here. It makes things a lot easier. So for instance, I mentioned XML responses. You can, using Data Firehose, you can convert XML on the fly. You can also compress it. You can aggregate it as well. So if you have a ton of tiny puts to your stream, records on your stream, you can consolidate those in a batch. It could be a time window or it could be a size window. So every 5 megabytes or 3 minutes, whichever occurs first, wrap it up and dump it to S3. So it's a reliable way to get that data to S3. And then I mentioned that this customer was looking to scale, and the reason they used API Gateway was having tons of different methods on this, but they also want to be able to scale this stream. And you could run into a case where you need more Lambda processors. So if you're familiar with SQS, you can do a batch size of 1 to 10. And that sounds kind of low, like a 10 message batch, but there's no limit to the amount of calls per second you can make to it. There is a limit to the amount of calls per second you can make to a Kinesis stream, but the batch size can be greater. You can have 10,000 up to 10,000 records. But we introduced a new feature called parallelization of Lambda, where you can have up to 10 concurrent Lambdas per shard in a stream. So if you have a stream with 10 shards, you could have 100 concurrent Lambdas executing on that stream. And each Lambda can take a batch of up to 10,000 records. So now you can start to really scale this out. But this actually ran into an interesting problem with this customer that I haven't yet gotten an answer to. So we're going to hit the limit of what I know with Kinesis and Lambda in a second. And if anyone here knows it, please let me know. I've reached out to like Kinesis specialists and stuff, and we're all working on it. So it's kind of interesting. The last thing I haven't done is try it out and scale it out and build it and see what actually happens. But it's kind of an interesting little corner case. So for Kinesis, each stream can have multiple shards, and a shard is effectively like a little dedicated, I guess you would call it, container, where it has a dedicated amount of, or a maximum amount of puts per second and ingestion rate, and it also has a maximum number of consumers that can be consuming from that. But the way to scale out Kinesis is through more shards. Kinesis leverages partitions, and these are partitions that are, they end up being converted to an MD5 hash by Kinesis on the back end, and then it uses that hash to allocate different messages to a different shard on the stream. So you can use one single partition with one shard, but that's a really bad idea. You want to have a ton of extra partitions. A good way to do this, if you don't have a kind of clearly outlined partition key, is to just give it a random one. And so you'd end up with like a GUID for everything, and every single message would have its own partition key. Let Kinesis figure out where it's going to put it on your stream and which shard on the back end. But this would be a better approach, where you have, say, each of these colors, and I hope if anyone's colorblind, I'm sorry, I didn't think about that until just now, but each one of these assume is a different partition key. The cool thing about this is that ordering, like I mentioned, was important. And Kinesis is going to keep order by partition. So if you see a blue one here, a blue one here, blue one here, and blue one here, if you read this whole batch, by partition, there's still going to be an order. So we've maintained order on this shard by partition key. So that brings us to what happens if you have two shards. Well, Kinesis is going to figure out where to place those shards by their partition key on the stream. So you can't end up with a scenario like this, where you have a green partition in shard 1 and a green partition in shard 2. What you'll end up with is something like this, where you have the red and blue partitions on shard 1 and the yellow and green in shard 2. And that makes sense, because now you can keep order per partition key in this case as well. Whereas up here, if you were consuming from this shard with the Lambda and consuming from this shard with the Lambda, how would you guarantee order? So this is the way that Kinesis does that. Everybody with me so far? Okay. All right, so now interparallelization, where you're going to invoke multiple concurrent Lambdas up to 10 on a given shard of a stream. So let's take this simple case here of one shard, and we've got 3 different partition keys, blue, green, and red. So Lambda 1 here is going to get a batch of blue, Lambda 2 is going to get a batch of red, and Lambda 3 is going to get a batch of green. And it's going to go until it fills up those Lambdas. So it filled up to the 10th one here and got there. It's not going to keep going because it can't fill up more. So now we have the same kind of scenario where we have 2 shards with 4 partitions, and we have 3 concurrent Lambdas that can invoke on a shard. What happens to that 3rd one? Does it just end up empty? And as far as I've gotten an answer so far, yes, it does. It would end up empty. These first 2 would start consuming the stream. They would take their batch size until one of them filled up. And the next one on this different shard would do the same thing, where it would fill up. So what happens, though, if you have 4 partition keys, but 3 concurrent Lambdas, and they're all intermixed? What happens if you overload a single partition key? What happens if you underload one? Where does this, we start taking messages from this queue down the line, and then we get to this 4th one. Does it get allocated to Lambda 3 here, Lambda 2, or Lambda 1? How does that work? And this is what the Kinesis team is telling me right now, which is that this 3rd Lambda, there's a batcher function in here that you don't manage. This is managed by the parallelization feature. It's going to figure out where to put these partitions for these given Lambdas. So you'd end up with something like this. Kind of cool, huh? So that is a kind of edge case to look at, where you've got to make sure that, one, you have a ton of partitions for a given stream. When you shard those out, Kinesis is going to figure out where to put those. And if you're leveraging the Kinesis consumer library, the KCL, it's going to handle a lot of that, the legwork behind the scenes of where messages are in a shard and the coordination between various workers on that shard. But this is a really interesting feature to keep your pulse on, which is Lambda scaling out through parallelization. It can really process this stream. And if you have 10 Lambdas that can each take a 10,000 batch size, you can end up processing 100,000 records every time there's an invocation. And Lambda can invoke every second on this stream. So this is a way to really scale this out. Plus, you can, as you invoke more shards to your stream, you can really scale out how Lambda works. Just be careful that if you have a ton of concurrent Lambdas invoking, that can affect your downstream processes too. So that is what I wanted to share with you today. Some kind of neat architectures I've seen in the field recently that are serverless in nature.
Thanks so much, Brien. That was awesome. I think we're going to switch gears here, and we're going to hear from James Curtis from CloudCheckr about a re-architecture project that we recently did. And again, thanks so much, Brien, for joining us today.
Oh, real quick, were there any questions before we split?
Great point.
Well, if you think of any, throw them in the chat. I'll be here for the rest.
Thank you.
And James, you've got the wheel.
All right. You guys able to see my PowerPoint here?
We've got it, yep.
Awesome. Cool. So I'm James Curtis. I'm a tech lead and member of the architecture team here at CloudCheckr. And like Alana said, I'm going to talk to you guys today about our transition from a monolithic architecture into a more modern serverless architecture. So quickly, I'm just going to give you guys an overview of what CloudCheckr is for those of you who aren't familiar. I'll give you a kind of just a review of what our monolithic architecture looked like, some of the motivation for moving off of that platform, and then I'm going to talk kind of about each module of our new platform and how it relates to some of the serverless services that are offered today. So starting off with what is CloudCheckr. CloudCheckr is a cloud management platform. We offer a suite of tools around inventory, cost, security, and compliance. We primarily work with both MSPs and enterprises in order to help them with invoicing, cost optimization, and like I was saying, security and compliance across the board. And like I said, we're kind of right in the middle right now, transitioning from our about 9-year-old monolithic platform into microservices and serverless. So our monolith was a pretty straightforward .NET web application. What we had on the front end was our ALB, which was just backed by EC2 instances hosting a .NET MVC application. Our data tier is primarily made up of RDS and S3. More recently, we've moved some of our larger data sets into Redshift. But then really the bulk of our processing is happening spread across an EC2 worker tier. So we have these basically Windows processes just installed on EC2 instances, orchestrated by SQS. But each of those is running these very just long running processes to load data in from our customers' clouds, analyze them, and write that back out. A couple statistics about the current scale of our application. Today we're running over 250 RDS instances, and across that we have over 7,000 databases. All that together, we have over a petabyte of allocated storage. And as you can imagine, running RDS at that scale is single-handedly about 40% of our AWS bill. It's by far the largest part of what we're running today in the monolith. For EC2, we're running over 140 instances across 3 regions. Over 50 of those are in the R512XL or larger. Those are those worker nodes that I was talking about where we're running those long processes. We're running about 1 million different jobs daily. And then in S3, we have about 110 terabytes of storage allocated and about 60 billion objects. So as you can see, we're processing a huge amount of data and handling that in EC2 and RDS today. Of course, these services at this kind of scale are causing us quite a few problems. We're having a lot of trouble continuing to scale out. We really can't scale out anymore. We're only able to scale up. So we're just getting larger and larger RDS instances, larger EC2 instances, and kind of reaching the limits of what we're able to do with these services today. Like I was saying, this gets incredibly expensive. RDS, like I was saying, is over 40% of our AWS bill today. EC2 is right behind it. And those are just those, until we started to break this all apart, we're just continuing to climb and climb as we continue to grow our customer base. Furthermore, deploying across this system was extremely challenging. Some of our deployments, again, we're in 4 different regions right now. Our deployments could take up to a day while we would shut off different pieces of the system. We're shutting down our workers, installing new dated Windows processes, bringing them back online, which is causing strain against our databases, et cetera. As you can imagine, with any monolithic code base, you get into a very complex web of code. So we might have changes to our inventory system that are going on and actually breaking our billing and kind of back and forth. And then finally, we just are seeing slow performance across the board, even though we can continue to spin up larger EC2 instances, larger RDS instances. We're only able to scale this platform to a certain point, and we're really reaching a point where we can't even throw more money at it to continue to scale. So with all of these factors, this is what's driven us to break apart pieces of our application first into microservices, and then much more recently into pure serverless architectures. So this is CloudCheckr 2.0, what we branded as CMX. I'm going to take this apart piece by piece, but just wanted to show you guys the big picture at first. We have our data ingestion, which is orchestrated by step functions. We have our data tier off to the right there. On the bottom, we have our API 2, which is a combination of serverless technology and a Kubernetes cluster running on EKS. And then our UI 2.0, which is a React application. So you can see kind of a mix of event-driven processing here. We have some serverless orchestration, serverless data tier, et cetera. So starting from the top, we have our serverless UI. Like I said, this is a React application. React, as you would imagine, is hosted in S3 and then distributed around the world by CloudFront distributions. For the UI, this has greatly simplified our deployments. It's just as simple as taking our React app, publishing it to S3, and then invalidating the cache. This gets picked up by our users within minutes of every deployment, and we're able to deploy multiple times a day as necessary. Being backed by S3 and CloudFront, it's almost infinitely scalable. Effectively no downtime, no matter where we're looking. Previously with the Monolith, where we had EC2 instances in that ALB, we would actually see instances where some of our larger customers would go and load a report and actually choke out some of the smaller customers that might even be sitting on the same instance. So we've completely eliminated that problem as well. Moving on to our API tier, like I was saying, this is a Kubernetes cluster hosted on EKS, fronted by API Gateway, and then primarily using DynamoDB as a data tier. But the more interesting serverless piece here is going to be how we're handling our event-driven processes. So although we do have requests coming in from the API Gateway, a lot of our background processing is being driven by events here. And what we're actually doing is, in certain cases, we have EKS publishing. In other cases, it's other processes, but we're publishing to one centralized SNS topic. We have a standard format for what an event is going to look like inside of the CloudCheckr system, but we will publish an event, say a customer is created or a new account is credentialed. And then we have SQS queues that are all listening to that SNS topic and filtering out messages as they come through. So if you can see off to the left there, we have the account changed event. So that's only looking for when an account is changed. And depending on which service is set up around that, we have certain ones where a Lambda function is going to consume that, consume events off of that queue and maybe update a Dynamo table. Or in certain cases, we have them actually going out and creating new step functions or other infrastructure per customer. We're also able to have a queue sitting there where maybe one of our services running on EKS is actually querying that or polling for messages there, pulling them down and processing. So we have a lot of flexibility across the system to route messages where we're looking and handle them with whatever service we're looking to do. And then finally, our serverless data ingestion. This is, I think, by far the most interesting piece of our new system here. Like I was saying, what CloudCheckr is doing, kind of our bread and butter is our billing processing. So we're going out to different providers, we're going to AWS, Azure, GCP, and pulling in CUR files, GCP, BigQuery, Azure billing, pulling these files down, processing them, applying our custom billing logic, writing that out, and then allowing customers to query it. And for those of you who have worked with some of these billing files, especially in AWS, the CUR file can get absolutely massive. We've seen some of our larger customers upwards of a terabyte of raw CSV on disk. So we've built this process where we have kind of two main step functions here. Off to the left, you'll see we have our manager, which is kind of our scheduling function. And then on the right, we have our processing. So on the left, we have this management function. It's just being triggered by a CloudWatch trigger on a cron. It's about 15 or 20 minutes. That's going to fire. That's just going to find out which customer step functions are ready to run based on a case of when they last ran and errors and such. So we have a Lambda going out to Dynamo to get that information. And then it, based on what it's getting back, is going to fan out into as many Lambdas as there are messages back. And that's all orchestrated natively by the step function for us. Each of those Lambdas in the fan out is then going to kick off individual step functions per customer. So we have per account in CloudCheckr. So each account is going to have its own step function where we're managing that data ingestion. So as you can imagine, we actually have thousands and thousands of these step functions that we're managing. This step function is going to start with an orchestration Lambda. So it's going to take the message that's coming in, and it's actually going to decide where to start in that inside of that step function. I'll come back to that in a little bit. But what you'll notice here is we actually have a step function that's made up of step functions. And in some cases, as you actually dig further into here, we actually can go 4 or 5 levels deep with some of these step functions. And this has given us a lot of power to create these little modules or microservices, if you each of them independently deployed and orchestrated as step functions. So what you'll see is we have things like our ingest and our pre-process step functions. Those are shared across the entire system. So we can do one deployment there without having to deploy to every one of these thousands and thousands of customer step functions. We're able to just keep the top level step function very generic. So that orchestration is going to start with our ingestion. Again, we have that same pattern of a Lambda, which is going to go out and how many files it's going to need to pull in. And then that's going to fan out into individual Lambdas. Each one is going to go and pull a piece of that per file into the system and save it in S3 for us. Our billing pre-process is going to follow a similar pattern. It's going to see how many files we pulled in, fan out into each of those individual Lambdas, and apply some of our pre-processing logic. Like Brien was saying earlier, natively, most of these files that we're pulling in are actually gzipped. That's not a splittable file format. You'll see that we're about to go to EMR. So what our pre-processing actually does here is it takes those gzip files and it converts it to BZ2, which is a splittable compression. So once we have those files in that BZ2 format, we have another Lambda that's going to submit a job off to EMR. This is where we get away from our kind of pure serverless architecture. We are managing a system there, but EMR being a managed service at least still gives us a lot of advantages. And we need to be able to run some of our larger long-running processes there. So some of these processes can actually take an hour or two in EMR, which kind of obviously exceeds the 15-minute cap that we have in Lambda. But we're doing just our heaviest load business logic processing there, writing that back out to S3. Billing process and post-process are going to be similar as well. We're going to take those individual pieces, fire that off to EMR, do some extra processing, and write that back out to S3. And then at the completion of all of this, once we have all of our billing logic applied, we're going to, like I said, we have our data in S3. We're actually going to fire another Lambda and transform that data into, send that data over to Snowflake. If you're not familiar, Snowflake is a third-party data warehouse tool, which is effectively serverless as well. It gives you warehouses that you can configure very similar to the way that you would configure compute for a Lambda. I've been talking kind of fast. Questions so far?
I'm curious if you switched up the language that you're using when you went to Lambdas.
In fact, we did, yeah. So, well, in certain cases, for all of our billing ingestion, we did switch away from .NET. All of our Lambdas are in Python now. Our Spark code obviously is in Python as well. Some of our Lambdas in the API 2 box there are still .NET Lambdas, .NET Core. But having this kind of highly modularized has given us that advantage of being able to pick and choose what language we're going to use where.
Did you find you can use Lambda layers?
We've not made use of them extensively in the application. I use them pretty constantly when I'm kind of writing one-off stuff to do some processing on the back end. But we haven't really tied that in with our deployment mechanisms today. We're still kind of just packaging and deploying natively.
So one thing I thought I heard when you were talking about this was that you may run like the data ingestion in individual accounts. So like the account where the data came from?
Oh, excuse me, per CloudCheckr account. So all of this is still happening inside of one AWS account, with our AWS account. Yeah.
Do you do multiple accounts to get around some of the per account per region Lambda limits?
No, we've actually, we've encountered per account Lambda limits only once or twice, and we've actually just requested increases and are well below the cap right now. Most of these Lambdas are firing in really, they're measured in milliseconds. They're happening so quickly. There's only kind of one piece of this architecture where the Lambdas are running for more than a couple of seconds. So although there are a lot of Lambdas constantly firing all the time, they're happening so quickly that we're almost never running into concurrency limits. And then because of the fact that they're orchestrated by step functions in play as well, we're kind of letting AWS handle all that scaling for us.
Have you taken advantage of like globals in the Lambda for like things like connection pools, or anything else, any other state that can be maintained between invocations?
Nope. Any state that we need to maintain in the pipeline, we're handing that state back to the step function for control. Each Lambda is running completely stateless.
Yeah, right. Because in step functions, right, it becomes part of the state, right? All right. Well, there was one thing we found out, and Amazon confirmed, was that once the Lambda container warms up, the globals in your code maintain their values, and so sometimes you can leverage that just for performance. But your stuff's running really quick anyway. So
yeah, and it's funny. We've actually done exactly the opposite there. We've bumped up against that as well, and in a couple of cases, we're actually just clearing everything out to ensure that we are maintaining completely stateless Lambdas.
Yeah. It's something that everybody's got to think about in their own use case.
Yep, for sure. So like I was saying, I kind of talked about each individual piece here, but this is once again the big picture of what we're doing. So once we're fully processed, once we have our fully processed data, we're doing things like we have our API 2 layer, querying some of that data in S3 using S3 select. We're reaching out to Snowflake for some of our larger processing. We have events generated by our Kubernetes tier, which are, like I was saying, firing off an account changed or an account credentialed event, which ties back in and creates pipelines for us. And then off to the right, you'll see we have customers using our React layer to query our API, which is then going to kind of cycle all through as well. So it's, even though each of these is modular, independently developed, independently deployed, the AWS services that we're using make it very easy to tie each piece together and maintain that independent state. Overall, by switching to this new architecture, we've seen the majority of our processing speeds improve by over 60%. Some of our longest running jobs have improved by over 90%. We've seen processes that are taking 4 or 5 days execute in about 1 to 2 hours on this new platform. But even more importantly, our costs have been reduced by over 90%. Again, our primary costs with the Monolith were EC2 and RDS. You can see our data tier being primarily S3 and Snowflake now is truly just kind of paying for exactly what we're using. We're not having to allocate extra storage in RDS that we're not using. We're not having to allocate compute that we're not, that customers aren't leveraging. Deployment times are reduced from hours or days down to minutes. Many of these Lambdas are deployed multiple times a day. And furthermore, when we have encountered bugs in production, it's so easy to develop and deploy in these individual modules that within hours, we're able to get bug fixes rolled directly out to production without any kind of hotfix process, just following our natural development cycle, whereas previously it might take a week or two. This architecture has been highly, highly testable for us. It's very easy to test these individual Lambdas. We have a lot of connection points in between these systems where we're able to inject data and test through. So for these event-driven systems, we're able to synthesize events and test individual pieces of the system that way, instead of having to buy actual AWS resources to trigger different pieces of the monolith. We're able to test each of these in isolation as well, either at the subsystem or the step function or the individual Lambda level. It's been extremely fault tolerant. So remember, I was talking about that kind of orchestration Lambda. We have the ability to start with that, we're able to start the step function at each individual state. So we can start at the ingest or the pre-process or post-process, depending on if we failed last time or if we have new data available. But furthermore, those eventing queues, we have dead letter queues set up off of each one of those as well. So we can retry and eventually even just capture an event if it's something that we can't process. And then even at the EMR tier, we're primarily running on spot instances. So if one of them fails and we lose a piece of the job, EMR is smart enough to manage that job at orchestration for us, pull a new instance online, and continue completely uninterrupted. And then finally, across the system, we've significantly improved our monitoring. I'm sure you all know with all of these new services that are coming out, there are a ton of monitoring tools out there, both native to AWS. We're using CloudWatch metrics extensively. X-Ray we're using constantly as well. But then tools like New Relic and Datadog also have just built-in functionality across the board. So every time we bring a new service online, we even get just default dashboarding out of all these tools that we have right at our fingertips. So it's made it much, much easier than trying to implement custom metrics in our Monolith or even kind of APM orchestration, that kind of stuff. So overall, we're in the middle of the transition, still kind of working our way through it, building out new features and functionality. But it's been huge wins across the board. You know, we're obviously very excited to continue with our serverless development. I'll open it up to some Q&A if people have other questions. And if not, feel free to reach out anytime. Thank you all.
Yeah,
Thanks so much, James.
I thought it was great to see some of the performance and other learnings that you got from the system.
Absolutely, yeah. It was even when we were doing just kind of POC of what we expected, building it out. We've been super excited kind of every time we've tested the system. The performance has kind of exceeded our expectations everywhere.
Nice.
Awesome. Thanks so much, James. And with that, we're going to switch gears once again, and we're going to turn it over to Scott Weber from Eagle Dream, who's going to talk to us about a project that they've been working on. So Scott, take it away.
Yeah, hey, good. I guess it's evening now. Good evening, everyone. Let me just share this here real quick. I don't think my talk will be anywhere near as long as Brien, and hopefully this works. Ring Central sometimes gets weird on me. You guys see the slides? I want to make sure it didn't switch screens on me.
Yep, see the slides.
All right, cool. So what I'm going to talk about is an opportunity with a startup that we've been working with about 2.5 years. And kind of the unique thing with a startup that I always kind of like is it's a clean slate, right? So we have the opportunity to jump sort of right to those cloud native things and see what how we can help the customer. So we're going to talk about a company called 5x5 Technologies and how we've worked with them to build out their web portal primarily. I'm going to focus on, but also talking about, I'll touch on a little bit of the back end and where we're taking things. So a little bit about 5x5. So they're doing some really interesting things with spatial computing and 3D digital twin models. So they use drones and go fly around the cell tower, which is, anybody who knows anything about radio frequency, that's a feat in and of itself with the signal power coming off of a cell tower. But use a drone with a 2D camera, take a couple thousand photos of that cell tower in a prescribed flight path, and then come back, create a 3D digital twin that's engineering accurate. So we're talking a couple 100-foot tall cell tower that's accurate to a 32nd of an inch. And then present to their customers, who are the cell tower owners and the cell carriers, that 3D model via a web browser, and allow that customer then to interact with that cell tower almost in a CAD-like way. So they can do things like, they can tell the customer, how are the antennas pointed? Are they, what is all the angles of the antenna? Are they pointed in the right direction? They can allow the customer to slice the antennas directly off the 3D model and go in and measure steel plate thickness. to determine, you know, can we go hang more stuff on the tower, right? So sort of the flow is, you know, a drone operator goes out, flies the tower, captures a couple thousand 2D photos. We upload those into an image processing pipeline that we built out for them. Obviously, this leverages a ton of S3 storage. They're currently using a third party, that piece of software that actually does the 2D to 3D conversion, but we've built a lot of step function controlled orchestration of lambdas, and then calling into this software and making it so that the software can just sort of spit out a result. And then we push all those images, the 3D image data that comes out, you know, we're typically dealing with around 100 gigapixel 3D image, throw all that data up into an S3 bucket along with the actual 2D image files, which we also have to be able to display, and then present all this up through a web browser. So as crazy as that, when we first did this, I was like, you can really do this through a web browser, but they had a working prototype. Turns out there's a package called 3JS, which plugs into Angular, I think, and allows you to actually interact with 3D things via a web browser. Kind of crazy. So just a little bit of background, like, you know, how is this even a thing, right? When you kind of think about it. So they're starting with cell towers. Turns out cell tower is one of the hardest things to do. And what you're seeing here on the slide is actually what one of the renders of a tower that they've flown ends up looking like, you know, in the web browser. So this is the 3D model with a screen capture off the web browser. You know, obviously we can understand having a human climb these towers is a lot of work, and they have to shut the towers down to send a person up because there's so much EMI coming off of these things. There's something like there's a shortage of something like 20,000 people to climb cell towers around the world. And they're just starting with cell towers, but they're going to be able to take this technology to pretty much any structure. So think of it as think of bridges. They're talking to other types of things like oil refineries where you can't get a human into, right? But you maybe need to see how everything's laid out, and, you know, something dripping on the ground, that kind of thing. They're also looking at some stuff to help, like what's happening in California with wildfires and identifying issues on the power grid. You know, can you identify transformers that are running too hot, different things like that. But the focus right now is on cell towers. There's a huge market for this. And again, there's a huge amount of image data behind everything that they're doing. So some of the things that we've helped them with on the bigger picture here, and then we're going to get into what where Lambda comes into this, is, you know, we've done some work with AWS around AI and ML as well, and we're actually kicking off a very big project with them around AI and ML. But AWS did some initial stuff where, to build the 3D model, like pictures that aren't part of the cell tower throw the modelers off, right? So you can imagine the drone operators got the drone out, sitting on the ground, they're trying to get ready to take off, and they accidentally start snapping some photos of the grass right in front of the drone, or the drone's flying, takes, you know, pictures of empty space. So we worked with AWS, built an AI and ML model that could basically just be a picture sorter. Does the picture contain anything that looks like the part of a cell tower or not, so that the 3D modeling software can converge fast. But let's take a look at what the front end for the web app looks like. In some ways, you know, there's some similar ideas here that James was talking about for where CloudCheckr is going with things. So all starts out with a big CloudFront distribution, especially with how much image data that they're talking about. It's an Angular built web application, so we're serving all of that up out of S3 buckets. All of the what we call asset data, so that's the 2D files and the 3D model files, are stored in a different S3 location. And what was kind of cool about this one is, I mean, it's truly serverless all the way to the back end. We're even using Dynamo tables. So there's about 136 Lambda functions today in production. We're using Cognito to handle all of our, you know, authentication work. We can tie it out to 5x5's customers' SAML system. So, you know, this is a SaaS application essentially, right? So we want to be able to tie out authentication to their customers' identity stores. We did a little bit of work on exposing an API, actually using GraphQL to expose, because some of the third parties needed to be able to the companies flying the drones needed to be able to just check on status of their uploads. Did the tower converge? Could we get a good 3D model out of it? Do they need to send a crew back out to refly the tower? But the meat of this is really in the middle, right? So it's API gateway to a fleet of Lambda functions to a whole bunch of Dynamo tables behind the scenes driving the whole application. This has been a really cool project for our teams to work on. And just speaking about cost for a little bit, they had their busiest month yet as they're growing. They still didn't break $100 in AWS cost to run this web portal, not including the S3 storage. But in terms of transactions through the API gateway, transactions on the Lambda functions, Dynamo, table reads and writes, all of that, they still haven't broken $100 a month to run this this architecture in AWS. Just opening up my chat window in case anybody has a question. So, I mean, in some ways it's kind of pretty standard, but again, we started this a couple of years ago. It's using SAM everywhere for deployment. It's using SAM local for the localized development of the team, the local development that the team is doing. The Dynamo stuff, in some areas, we've gotten into some pretty sophisticated designs of the Dynamo tables to be able to answer the questions that we're asking to it. And then doing the GraphQL piece was actually a pretty interesting thing for the team to stand up. And the thing I love about GraphQL is this idea of, you can really optimize the communication, because GraphQL, you can say, well, maybe I only need 2 bits of information about my customer as opposed to the 30 maybe that's in the database, right? You can just get those couple bits that you need back and optimize your communication pathway. The backend processing is, the architecture diagram for that would be pretty horrendous. But again, we're moving all of that to wherever we can. There's Lambda functions. It's a little bit more complicated because the 2D to 3D software that actually does the tower renders is based upon Windows. So we get into, but it has an API, so we can kick off jobs essentially to the rendering engines. And, I said they're spending like sub $100 a month on their web portal. They're spending, last month they spent $90,000 a month on that type of order on EC2 to do their tower renders, right? Because it just takes a lot of horsepower to be able to do these types of renders. They're running like G4 machines with the graphics cards and everything. But the back end is moving to step functions, Lambda functions where possible. There's a lot of image processing and manipulation where we got to extract metadata and different things. As the files arrive into an S3 bucket, it's one of those cases where there's just way too many files to try to manage them natively in S3. So we're using Lambda functions to build out the metadata into the DynamoDB tables so that we really know what's in S3. Pretty aggressive on lifecycle policy in S3 as well, to push the assets as soon as possible over to Glacier, so that we're only, we're trying to optimize that as much as possible, because it does grow pretty fast. Any questions, comments on the architecture? All right. Yeah. So where are we going with this? And this is I think one of the nice things about the orchestration you can start to do with step functions and Lambda functions and things is, one of the things that they need to start, that their customers are asking them to start looking at is, can we help detect cracks and rust on these towers? So think about, we've had a very active hurricane season, right? So one of the things you'd like to do right away is be able to fly a tower and see, did it suffer any structural damage? And then it's very common, sort of the pattern is these towers need to be inspected at least on a yearly basis. So from flight to flight, can we tell if crack growth has happened? So now we're starting to get into the ML area where you need the machine to be able to talk, to be able to start to notice these types of things. So you start to get into, can we train the machine to help do some of this analysis and take the human out of it? Interesting thing, this is sort of, it's not a point cloud, but that's the way I tend to describe it. So This is the first phase of a reconstruction of a tower, and these yellow squares actually represent the flight path and where a photo was taken of the tower on the flight path. And then this sort of point cloud thing is actually the picture itself in space of that part of the tower. And so this is like the first step to a render where we want to say, did the tower converge, and can we sort of squint at it and say it's a tower, right? We don't have like, you know, it's not at a 90-degree angle and weird things like that. Believe me, we've seen some pretty weird things. But just give you an idea, this is like stage one of a rendering. Then you send it in to really create the full 3D model. But so we're really starting to explore where can AI and ML fit into all of this. And we're actually going to be doing a project that's kicking off here soon. Within the next month, we already started the development work so that they could label images. But believe it or not, there's a big issue in the cell phone tower space of an entity owns the tower and they lease out space on the tower, and they don't know what the carrier might have put on the tower. And they want to be able to charge the carrier based upon what is on the tower. So we're working on developing an AI model that can recognize what's called tower mounted equipment. So think about ingesting a couple thousand 2D photos and building a manifest of what we see is on the tower. And then the next time the tower's flown 6 months or a year later, can we diff those manifests and not have to have a human trying to like say, well, this is antenna ABC and it wasn't in this position before. To scale this, you got to have the machine do it. But with pipelines based upon step functions and branching logic, you know, it's going to make it a lot easier to start to plug these things in once we can develop this model. And that's really it for me. Like I said, I knew I was going to be a lot shorter than everybody else, but this project I think is interesting. Yeah, we're using serverless all over the place for the front end, serverless in the back end, but I think it really speaks to the flexibility as you're building out a new solution to somebody for a customer, you know, insert branching logic into, you know, a backend pipeline or a backend step function to add a new feature. We're able to iterate extremely fast on front end features for this customer as well. And I think that's owing to the serverless nature of this is, you know, your blast radius is so small with Lambda functions and things. So I'm going to stop there and see if there's any other questions.
Awesome. Thank you so much, Scott. I want to thank Brien for being so philanthropic as to join us from New Jersey here in our humble Rochester AWS users group. I think it's going to be great that we have the recording of this to circulate afterwards. James, much appreciated for your portion of this session. I think even as your coworker, I learned a tremendous amount about our re-architecture project. And Scott, that use case was incredibly cool. So I think this was a good session. We solicited feedback from everyone in the group in order to plan this out, talking about serverless. And I think that's going to be a trend going forward. We're going to take advantage of the fact that we have this work from home world that we live in. I know Zoom meeting fatigue is a real thing, but hopefully every couple of months we can get together and have a really interesting topic to discuss. So we will be reaching out to all the members of the group to get feedback on what might be a good subject for our next session. But thank you so much, everyone, for coming today and for sticking with us. And thanks to our presenters again.